Okay. I am John Beckmann, Professor John Beckmann, Dr. John Beckmann, the father of sin, the transgenic mother of sin, your hostess with the mostess. So I do have some updates this week on the CI and evolutionary algorithms. I had some intellectual breakthroughs on the project over the weekend. I spent some time thinking about properly how to model the toxin antidote fitness, because that needs to be solid. That the framework of how you're measuring the fit, or how you're selecting for the fitness on the TA systems, needs to be solid. And if you watch the first video, so this is part 2. If you watch the first video, I describe a little bit about modeling the fitness of TA systems, but I realized after I discussed that, I really only got half of the key components. So what I discussed last time is if you are to model the fitness of a TA pair, so you have an antidote and a toxin. Get some skull and crossbones. If you were to model the fitness of a TA pair, what I discussed last time was one of the key components is the binding affinity of the antidote to the toxin. And I constructed that as a key component to select for. You want to select for high binding affinity, a high pairing between the schema of the antidote and the schema of the toxin. And the reason for that is because as a toxin antidote, you would not want an antidote that can't rescue properly. The best antidote is one that can fully rescue your toxin. There's no advantage to having an antidote that doesn't fully rescue your own toxin. Okay, at least in my system. So that was how I was describing this, and I described the algorithm of how I was going to calculate this value. And essentially, the gist was you have a sliding window of the one schema on the top, another schema on the bottom. You slide this, and each slide you check all the values, and you calculate some ratio or some value of essentially how many matching pairs you have. And the way that I calculate this at the end is I take the sum of the matches divided by the length of the antidote. And I described the rationale for this. We can't have systems that are infinitely getting larger, because in biology we can't have infinite length. And all this would select for, if you allowed infinite length, if you had no constraints, all this would select for is infinitely long pairs that are going to match at some place. Okay, so I described having this constraint dividing the sum of the matches by the length of the antidote to sort of like force pressure on the antidote to bum its code to get smaller and smaller. And so I set a minimum length, and actually now that I've been simulating this a little bit, it's working. So as I start running the simulation, the antidotes, you can see if you measure the average length of the average antidote, it gets smaller and smaller and smaller, and it constrains to the minimum length, which is, I think, what we see in the biological system. So that we always see the antidote in CI, we always see the antidotes as much smaller than the toxin. So I think that that's fair, and I think this is an accurate representation of 1/2 of the equation of the fitness of a toxin antidote pair. My mistake was that I was not modeling the second part of the toxin antidote pair, which I discovered over the weekend through thinking. The second part of this is, which is obviously so obvious, this is only measuring the fitness of the antidote. Okay, I needed some mechanism of measuring the fitness of the toxin. So I figured out how to build this over the weekend. So in the way that CI works, the way that the system that I study works, is within the toxin gene. So if you have this long gene, proteins are constructed of different domains, and the different domains do various things. Okay, and in these toxins, in these cytoplasmic incompatibility inducing toxins, there's what I call the warhead domain, which is usually on the C-terminus of the proteins. And this is the enzymatic domain. So if we're talking about SIDS, this is the dub. Or if we're talking about SINs, there are nucleases. And we'll talk about these differences in a second because it's important to the modeling. But essentially, the gist for the schema theory, what you need to know is these warhead domains are they're the parts of the protein that does the killing action. Okay, so you could imagine if you got a mutation here or here or here, you might still have a completely effective toxin, because as long as the warhead domain is intact, it's still doing the killing. Okay, that's an important point, is that there's a selected region of this protein which causes the killing. Probably upstream, and certainly there are other parts of this protein that are important for certain functions, but in the modeling of a classical TA pair, I think this is an interesting component to add in, the warhead domain, okay? And within CI, it's even more interesting in the sense that some of the toxins are dubs, and some of the toxins are nucleases that have two warhead nuclease domains. So nuclease 1 and nuclease 2, or C-terminal nuclease domain or N-terminal nuclease domain. So the other thing that's interesting is, okay, let me make this even more complex. So these are the SIDS that have the dub warhead domain that does the killing. These are the SINs that have the nuclease warhead domain, where there's two nucleases which putatively do the killing. And there is a third type of warhead that has both. So it has a nuke 1, a nuke 2, and a dub domain. We call these affectionately Cindy's. We love the Cindy's. Cindy. So this is an interesting biological system, because what's happening in CI, and I'm not clear, again, I don't understand these forces at all, which is one reason why I'm modeling this. But what's interesting is that in some of these toxins, there's multiple theoretical warheads. It's not just one warhead. You can imagine why you might want redundant warheads. It might be useful to have redundant warheads if one warhead gets damaged, the second one would still work. But again, that implies sort of some kind of like some selection, some kind of like utility to the warhead domain, which is sort of like, again, like if you watch the last video, that's sort of like counterintuitive to what some of the other modeling has said. So it's important for me to model this to build this into my model, okay? So the way that I constructed this is, as I construct the antidotes, I reward them for assembling catalytic domains. And I can define these catalytic domains as regions of order within the schemas. So again, in the previous talk, we talked about constructing these random toxin antidote pairs just based on bits. So I gave them 0s, 1s, and 2s. 2s would be a don't care. So these are sort of like the language that they're using, synonymous to or analogous to base pairs of DNA, or perhaps codons that code for amino acids, 0s, 1s, and 2s. And so I can artificially just imagine a dub domain, a dub catalytic warhead domain that's perfectly active. That means it kills at 100% ratio. Everything that's expressing this thing without an antidote dies. That domain can be written as an array of 9 zeros. I'm artificially just defining this. I'm saying if this thing evolves, if this thing pops up in the toxin domain, I'm counting this as a catalytic domain, and I'm going to reward them for developing this, because all toxins want to kill the host in the context of not having the antidote. And the way that you can select for this to evolve is you reward them for getting closer and closer and closer to this schema, okay? So again, I built a sliding window algorithm that's analyzing the catalytic domain, except up here you put the toxin, and down here you put the catalytic domain schema and the 9 zeros, and you just do a sliding window again and look for the zeros. And essentially it just tallies, well, how many consecutive zeros are there in a row, or not necessarily consecutive, but within the schema. Let's say you had if you had the perfect dub catalytic domain, 9 zeros, you would get a point for each zero, 9, divided by the length of the catalytic warhead, 9, which would equal a perfect 1. Okay? If you had, say, imagine as you were starting to evolve this toxin, imagine you had a scenario where you had a toxin that looked like this. This would get a tick mark of 1, 2, 3, 4, 5, 6. 6 zeros. 6 divided by 9 is about 0.66. Okay, so then this one would be rewarded 0.66, whereas this one would be rewarded 1. So you can see how now this is going to select for the selection of these toxins to develop this catalytic domain, which is what I want, okay? Because that's what the toxins would want. It would want to develop these catalytic domains and hold them conserved, and that's actually what we see in the wild. We see these domains are conserved. They don't want to get rid of their warhead domains. And all the nucleases are typically conserved, and all the dubs are typically conserved. Okay. That makes sense. Now, the interesting thing is I add in a little bit of complexity here based off the biological system. So not only do I allow them the ability to evolve the dub domain, I also allow them the ability to evolve a nuclease domain. Okay? So I define the nuclease domain as just exactly opposite. 1, 1, 1, 1, 1, 1, 1, 1, 1, 9 ones. This is going to be my artificial definition of what constitutes the nuclease domain. And the reward for this is exactly similar. If they have 6 ones, they would get 0.66. If they have 9 ones in a row, they would get 9 out of 9, which is a 1. Now here's where I build even more complexity and it starts to get interesting. So as I'm modeling this fitness, here's where the biology is informative in building this model. The question is, if you have a protein, a toxin, that has a perfect dub domain that already kills at 100%, there isn't necessarily an extra added advantage to having an extra catalytic warhead domain because you can't kill beyond 100%. Does that make sense? Like you cannot kill more than 100% dead. Once you're dead, you're dead. You're dead, bitch. So I can't select for this by giving extra added fitness for killing. Okay, the only way in the model that this would give some kind of an advantage is that perhaps this would somehow build in a redundancy that protects against mutagenesis, or perhaps it protects against recombination or something like that. Okay, but you don't get infinite fitness points for building toxin warhead domains beyond something that kills already at 100%. Does that make sense? So the way that I actually calculate the other half of this fitness is the algorithm looks for a dub, does a dub check. If there's a dub, it essentially gives a variable 1 point, or some 0 to 1 scale based on how well it fits that schema. And I'm using this as an analogy for the percentage of ability to kill. Okay. Then it does a nuclease check. And if there's a nuclease domain, it again rewards a separate variable that holds this. So there's a variable in computer science. If you don't know computer science, you might not know this. But there's some class variables that hold this value and hold this value. Okay. And then there's an algorithm that checks, is there a dub? Yes. Is there a nuclease? Yes. And it essentially calculates the fitness, but will not allow the fitness bonus for toxin to go over 1, because you can't kill beyond 100%. So it's essentially like with what I have, could I kill 100%? If yes, then you get an exact 1 for the toxin fitness. Okay, so essentially you can see, and now you can see how a Cindy might evolve. A Cindy might evolve from, at least in the model, it might evolve from a dub that is not fully formed yet. So perhaps you're only getting like 0.6%, 0.66 plus fitness bonus for this dub that only kills at 66% efficiency. And then you start evolving this nuclease, which kills at 0.33% efficiency. These combined together might kill at something close to 1. So these are how, in theory, like a Cindy could evolve, or something like a Cindy could evolve, where you're evolving some extra order in domains in addition to the dub or in addition to one nucleus. And so what I like about this, it allows the possibility to evolve separate nuclease or dub domains in combination, or combination of the two, but it doesn't select for it purposefully, but it allows it. So in future scenarios where I start really evolving the patterns of these things, it will have this choice to be able to do this, if that makes sense. If computer algorithm can have a choice, if it's strategically advantageous, these things will evolve in the system. Okay, so in final conclusion, this was the whole other half of the fitness equation that I had not even thought of as I described that first video. So in final, the definitive fitness of a TA system in the model can be a max score of 2. Okay, it's a sum of the antidote fitness, which is essentially the binding equation, which can be a max 1 if it's a perfect match between antidote and toxin, plus if you have at least one catalytic domain that's perfect, or some combination that adds up to perfect, you can have a toxin fitness of 1, which equals 2. Okay, so as I run these simulations, you're going to start to see fitness values that are like converge on like 1.5 or like 1.8. It's some combination of antidote binding and toxin killing power. So essentially, I've now completely modeled the fitness of a TA pair, and the proof of this is in the pudding that as I run the simulation, these things do evolve. So this is what I've wanted to build as a theoretical representation of the biology in the field, from which I can work off and start to probe hypotheses. That sounds very vague and ambiguous, but you'll see with a little bit more clarity as I move forward in the project, as long as you understand sort of how I'm calculating this fitness. Okay, so it's also worth, before I start talking about running these experiments and analyzing the data that's coming out of these experiments, it's worth me describing my mutation method and my recombination method. So I described how I'm allowing these things to evolve. And so let's describe how I wrote the algorithm of mutation. Okay, so the mutation algorithm has 4 parts. I'll write this out in very, very bad pseudocode. Okay, so there's a coin flip that can flip. Essentially, it's a 4, or a dice perhaps would be better. It's a 4-sided dice, but I call it coin flip. That can give you 0, 1, 2, or 3. Okay, so the first you just flip a coin or roll a dice. That will give you 0, 1, 2, or 3. If you get 0, nothing happens. So this is every generation where I'm selecting parent TA systems, mating them, and mutagenizing them to evolve new things, new schemata. This is the mutational process that's actually occurring. Okay, so there's a coin flip. If it gets a 0, nothing happens. You don't mutate the TA child. Okay. If you get a 1, you do a bit flip. So a bit flip is just it randomly, so these toxins and these antidotes, I should also say there's a coin flip too. There's a second coin flip that decides whether you're mutating the toxin or the antidote. So everything here is randomized. Like Do you mutate at all? Random roll. Do you mutate the toxin or the antidote? Random roll, etc. This is kind of the thinking. Okay. So if you get a 1 on the first coin flip, you do this bit flip, which is essentially like, let's lay out the toxin or the antidote, the schema, whatever it is, blah, blah, blah. Let's pick a random index. Let's say this one gets picked. Go to that spot. If it's a 1, change it to a 0. If it's a 0, change it to a 1. That's a bit flip. Okay? If the first coin flip lands a 2, that's an insertion. So the same thing happens. Pick a random index. Now flip a coin. Are you going to insert either a 0 or a 1 or a 2? Pick what you're going to insert and then pop it in at that random index. Okay. The last coin flip mutagenesis possibility is obviously then deletion, which is if you get the 3, go to a random index. Let's say it's this one again. Delete that base, remove it from the array. So I've built in here a couple different mechanistic possibilities. I've built in the power to do nothing, so that it doesn't mutate. I've built in the power to change individual bits in the schema. I've built in the power to make an insertion, which is increasing the length of a toxin or an antidote, and I built in the power of deletion, which is decreasing the length of a toxin or antidote. So if there's any advantage to getting longer or getting smaller, it will find it through this process of mutagenesis. Now, the final thing I have to add, which I have not added yet to the algorithm, but it's going to be important for later biological studies, is I have to add the potential of a catastrophic mutation. So, which would be essentially like a frame shift. So right now, if you just do a bit flip in like a catalytic domain, it's just going to reduce the killing power by a tiny amount. Like if you bit flip a 1 and change it to a 0, that would just reduce the catalytic site of a nuclease by like 0.1 or whatever it is. Okay, so it's not building in the possibility of a catastrophic mutation, which biologically, oh my God, Amber Alert. Don't tell me that, oh my God, I got an Amber Alert and it like shut off my video. Not that my video is more important than an Amber Alert, but I don't think there's anything I can do about the Amber Alert because I'm sitting here in my office. It's a killer mood. Anyway. Okay, so I was talking about mutation. The final thing I have to build into this is catastrophic mutation, which is equivalent to a frame shift mutation or a premature stop codon, which essentially pseudogenizes the gene. Pseudogenized, which essentially means you get this mutation, your fitness is automatically going to drop to 0. It's a catastrophic mutation. I have to build this in, and I will build that in. Okay, so there's a lot of possibility in the mutagenesis. Now, as we're evolving these things, we're also sexing them together, which is recombination. So I built an algorithm to recombine them, which is, the term for this is single point crossover. This is the simplest recombination algorithm. So you have the chromosome of the schema of a toxin. You have the chromosome of the schema of the antidote. And there's a dad and a mom. So let's do mom as red. It lines them up and it rolls a dice to pick an index. So let's say it picks, let's say this thing is 100 base pairs long. It picks index 55. Okay? Then what it does is it just instantiates a new array, a child array, which is now the black schema to base 55, and the mom schema to base 100. This is just a single point crossover. So the random variable is the index, picks an index, and then it just crosses them over. And then this becomes the child toxin. And you do the same thing with the antidotes. So you create a child toxin and a child antidote, and these children are then a new TA child pair. So this is how offspring are produced. And in the actual algorithm, you do the recombination first. You do parent selection. You do the recombination, which is simulating the sex and the development of children. Then you do the mutagenesis, so you mutagenize the children. And then you combine them all now into a new pool of adults. And then you do the survivor selection to see who survived based on the fitness, which I now have already all described. Y'all understand the fitness function. Okay. So that's the gist. I'll try to go to my other computer here and initiate a screen grab here of my other computer so we can walk through some of the code a little bit. Quickly, I'm not going to like run through like all the code. I just want to say a couple components because like it's built. So when you look at the components, right now there's just two classes and then a main driver. So there's a main driver which is running the evolutionary program. Okay, so it's instantiating population of 1,000 TAs, and it's picking the parents, running a recombination, running the mutagenesis, running the survivor selection, resetting certain variables, and then repeating. That's one generation, and then it will repeat generation for as many generations as I want. Okay, there's a TA class, which all the things that I've been describing are built now into this TA class. It is, let's see how much effort I put into this. 256 lines of code long. And then there's a CI Evolutionary Algorithm class, which is essentially running all the evolutionary methods that the main driver pulls from. And that is 208. So about right now, about 500 lines of code in complexity. So the interesting thing that we talked about last time is I'll run this now so you can see what it looks like. So if I run the main method, it's going to initiate the simulation, and it takes a little bit of time to initiate all the initial TA population. Okay, and then after that, it's only producing 100 children. So essentially, when you run evolutionary algorithms, the highest cost here it's going now. The highest cost in terms of computational time are always the fitness evaluations, and we talked about that n-squared algorithm that I wrote, the sliding window, which computationally, if you're doing it 10,000 times, takes a little bit of time. That's what's taking time, and it actually is taking way more time than I thought. So each time you see it click in advance, it's doing fitness evaluations for a population of 100 new children TAs, and then selecting survivors, and it's taking, let's count it, 1, 2, 3, 4, 5, 6. It's taking 6 seconds to evaluate the fitness of 100 new children and run through an entire generation. So there's something here that's really slowing down the program. I have to do some clocking studies to figure out which algorithm is really slowing it down, and then see if I can bump the code or see if I can speed up the algorithm a little bit, because this is way too slow. When we wrote the GPAC, when we wrote the Pac-Man playing games, it could play a whole game in essentially like a second. So something about this seems a little bit too slow. I'm gonna have to get somebody to look at my algorithm and see if I can speed them up a little bit. But as you can see, if you look at these parameters, so it's already significantly gone. Some of the parameters that I'm measuring are the highest fitness achievable. So I've already reached a 2.0, which is a maximum fitness. So this thing has already in, how many generations is it? Somewhere I'm clocking the generation 19. Within 19 generations, it's already evolved a perfect TA system, and probably faster than that. And what you see here is I'm clocking the average toxin length and the average antidote length. So there's going to be a bunch of parameters that I'm going to monitor as I run these simulations. This is just a minimal amount of things that I've had time to code to monitor right now. But one thing that's interesting to measure, because I've allowed the ability to expand or decrease the size of the toxin, it's what you're seeing here is exactly the prediction that my hypothesis suggested. And maybe this is because this is how I programmed it in terms of like the selective fitness. But what I suggested before in the past was what would happen was the toxins would obviously evolve to the biggest length because they want to be big so that they can have a match for their antidote. Wherever the antidote can match, like they just want to evolve a big section because there's no cost as long as the warhead domain is there really isn't a cost of them getting like longer. So they're going to evolve to the maximum length so that they can find the binding. And then the antidotes want to get smaller and smaller and smaller because to the minimum length because they essentially just want a tight binding and they don't need anything else beyond that. And once you bind to sort of like a threshold level, there's no benefit to extra like infinite tightness binding. Like once you have a threshold level of binding that is sufficient for 100% rescue, you don't want to rescue beyond 100%. So they're going to evolve to a minimum length, essentially. And the way that the algorithm is calculating the fitness, like it's not penalizing them for that. It's actually penalizing them for being too long. So essentially how I thought the algorithm should work is how my algorithm is working, which is, I guess, suggestive that I can write code, but it's not yet suggestive of anything necessarily biologically relevant in experiment 1. Okay, so experiment 2, where I start evolving these things competitively, is where interesting biological phenomena might arise in the computer. Okay, so don't take this too seriously yet. Let's see what happens with experiment 2 and as I look at different parameters to measure. So it's working. It's working according to the plan, and now the tests can start, and I can start building more complexity and doing different things, measuring and looking at different things here. All right, I will end it there to not bore people too much with details. Okay, so if you're liking this public research experiment, hit like, hit share, hit subscribe, join the channel, join the fun, write some comments, give me some criticisms, although not yet, maybe perhaps nothing yet quite to criticize. We'll wait till we start making some outrageous conclusions to see who we can troll here. Have fun. Okay, end it there. Have a good day. Good Wednesday. I am out.
I shall meet death head on. Decade, you've got to get out of here. Beware foul demons and beasts. There are many foes here. The time has come to cleanse my mind. This monastery reeks with evil and corruption. I hate staining my hands with the blood of foul sorcerers. Eternal suffering would be too great for you, Diablo. Let the